Hi, I'm David, founder and CEO of Cerebros. Today I'm going to present a technical demo of our novel LLM architecture, Cerebros Not GPT. We're going to build a proof of concept scale model with around 52 million parameters, and we're going to build this from scratch and train it in a CPU-only free tier Google Colab and Jupyter environment. The fundamental challenge with LLMs today is quadratic complexity timing. This demands massive GPU clusters, and that makes training a custom LLM out of reach for all but a few. But what if this assumption is no longer true? What we're doing today is made possible because of our sub-quadratic novel LLM architecture. This trains in ON complexity timing rather than ON squared. During training, we've scaled this up on a much larger data set on our server, but for this demo, we're going to train this on only 30 samples, 30 text samples, and we're going to get back correct text completion. So this isn't going to build itself, so let's get started.
So we're going to do the training in two phases. Neural architecture search phase, which is stage 1A, and stage 1B extended training. First, we're going to clone the repo, set the working directory, we're going to install the requirements. Note that there are two requirement files, requirements.txt and CI/CD requirements.txt. This will take a minute. All right, perfect. So we restart the session. Confirm we still have the repo present. And set the working directory again in the new session. Double check we're in the right place. Import the required packages. Perfect. So we have some constants that we set. Number of samples, we're going to do 10 in stage 1A and 20 in stage 1B, the second stage of training. We set some additional constants that basically control how much we're spending on computation. Now we're going to set the parameters for the neural architecture search. This basically sets the range of how many layers, the density of connectivity within the graph topology, and so forth. Now we're just going to set the parameters for the second stage of training. Now we're going to prepare the data. So, pre-processing the data, we're basically expanding one sample into one text sample into one list of tensor, or one tensor for each index position between the length of the prompt and the first occurrence of a pad token or the end of the sequence length. So basically, we're expanding this into one sample that has the cumulative sequence of tokens and one label that has the next expected token, and doing that over a sliding window that basically the label is always going to be the next expected token, the sample is always going to be the cumulative sequence up to what was predicted, what was expected to be predicted for the last token. Now we're setting up the base embedding model. So this takes the tokens and applies an embedding, then an interleaved rotary positional embedding. We go over what this looks like, but you can read that in detail in the repo. Now, this is what the actual neural architecture search algorithm parses. It's a list of dense layers that are resembling what we just saw. That was actually a printout of a real graph. The green nodes are input nodes. Blue ones are concatenate layers. Pink ones are hidden dense layers, and red, the red one was the output layer. Now we are actually training and running the neural architecture search. So this is going to try three different permutations of layers. It runs these in. It basically sets up a grid consisting of a randomly chosen number of rows and a randomly chosen number of dense layers on each row, and then it tries to optimize the vertical and lateral connectivity between all of those dense layers. So basically, the tokens go through the base embedding model, then it goes through this lattice of dense layers. And this will take a few minutes, but not long. So again, this is the stage 1 model training. So basically we're running the neural architecture search, and we're doing, for the purposes of this vanilla demo, we're training this on 10 text samples with a sequence length of 40. This is obviously a very small data set. However, we've run this scaled up much higher. We're just running something that will demonstrate in a CPU only environment, a small scale CPU only environment that you can train this and get it to actually complete sentences with this little of data. And on this modest hardware that we have in the Google Colab free tier, CPU only instance. And actually this very script, another version of it, is run on 4 CPU and 16 gigabytes of RAM in our CI/CD testing. Whenever we make changes to our repo, this runs as a test. So we've completed one LLM that's been trained. It's going to train 2 more, and it's going to go with the one that had the lowest perplexity score. And again, you can run this notebook for yourself. You don't have to have, deep technical knowledge to run it. It's already set up. There are no fill in the blanks that need to be completed. It's just ready to run and see it, see this train for yourself. So we're about a third of the way through the second LLM that this is training. 29 out of 41 epochs. This one we can tell is probably not going to be the one that this is going to go with. The one we had before did better than this, but it's going to try, it's going to complete this one, and then it's going to run one more. Alright, 2/3 of the way there. Training a third one. 52,476,644 parameters in total. Almost there. All right. And momentarily, the results will print out. All right, and it looks like the best perplexity score we got in the first phase of training was 7.87. So this is what the actual code for the model wrapper looks like. This is the class that we basically wrap the model we just trained with to make it able to generate. It basically acts like autocomplete on repeat. We trained it to be able to pick the next word, and now we're basically adding a loop that does that on repeat and adds sampling, scaling and sampling. So we have temperature scaling, we have presence penalty, frequency penalty, scaling, top P, top K sampling, top P sampling. So you can read about that in detail in the notebook. So now we're generating, now that we've applied the model wrapper to the model that we have trained. And momentarily we'll look at what some of the text that this has written looks like. We have this running with a couple of different settings. You know, as far as the parameters for the sampling, but as you can see here, we wrote the prompt, and the response is correct. So now we're going to proceed to extended training. We're going to continue training the same model on 20 more samples. And we're going to use a streaming generator dataset object, which is going to stream that pre-processing that we did, the same pre-processing that we did in the first stage that expands one text sample into many samples of tokens, which are paired with the label for the next token that's expected, which is going to train it to call what the next word should be given the new data set that it's being trained on as an extension of the original data set. We're recompiling the model, and we are setting up an early stopping callback, and we're setting up a custom learning rate scheduler. Specifically, it's a cosine annealing with restarts, which we added functionality to it to add warm-up steps to it. So now we are training, we're proceeding with the stage 1B training. So we are continuing foundational training on that extended data set. And for the purposes of this vanilla demo that we're only training on, a few CPU in a modest hardware environment, for the purposes of that, we're only using 20 text samples right now. But obviously, in our more scaled up tests, we've used much more than that. And you got a warning there because of the stop iteration callback. That's normal, that's to be expected. And now it's continuing with the second epoch. And this will be a bit, but anyway, it's going to continue with the training, and we will watch it train. So as you notice, there's a little bit of gradient shock between, the first data set and this data set. You start out with a pretty high perplexity score, but it will go down. Just takes time to stabilize. like we're about halfway there now. It looks like we're about 3/5 of the way there now. And if you notice, there's a little bit of an oscillating pattern in the perplexity metric. And that's kind of by design. The cosine learning rate scheduler is going to have that effect. All right, and now we are under 30 on the perplexity. Almost there, epoch 52 of 53. All right, the last epoch. Perfect. So the early stopping callback kicked in and did its job and restored the weights back to the best epoch. Well, in this case it was 53, but in any case, we have a perplexity of 29.64. So we're going to generate some text from the updated fine-tuned model and see what the text looks like. Obviously, with the perplexity of 29, it's not going to be quite as it's not going to write quite as well as it did on the last one. This would obviously need some optimization, and obviously we would be training it with a lot more than than 20 additional samples. But in any case, it is this is a proof of concept demo trained on a few CPUs, so this is about what you can expect here. Now we're going to save the model in the tokenizer. Then we're going to do a test to verify that we're able to serialize a working copy of that model onto another module. It's going to call a separate script for testing that using subprocess.run. And it's going to read in this .keras file that we're saving and verify that it's able to load that, set it up, and is able to run it successfully and get an output from it. Of course, this is writing probably, I don't know, half a gigabyte to disk, so it's taking it a minute. Okay, perfect. Now we do the serialization test. Make sure that we're able to import that and set it up and run it. And momentarily we will know the moment of truth on that. And there we have it. That appears to be successful. And that's what it takes to build an LLM from scratch using our model architecture.
So there you have it. We demonstrated a complete reproducible pipeline for training a generative LLM on only a few CPU from scratch. One that you can try yourself just by following the link. I'm David. Thanks for watching, and I look forward to the technical discussions that may follow.